energy production. The way our sun produces energy is through the process of fusion. And the definition of fusion is to join two nuclei together to make a heavier nucleus. How heavy a nucleus is depends upon how many protons and neutrons are present. So when you're combining two nuclei, then you are creating something that has more protons. So more protons is going to be heavier. Now, in order to do that, you do need very high temperatures because, recall, proton has a positive charge, and like charges repel. And so the only way you can overcome that repulsion is to get them moving fast. Because the faster they move, the more likely they are to actually collide and not repel. And the way you get them to move fast, you make them very, very hot. So these high temperatures mean fast speed, which means it can overcome the repulsion. Now, in the case of our sun, what we're actually combining are hydrogen atoms. And when we combine hydrogen atoms, which have one proton each, what we produce is a helium atom, which has two protons, plus some neutrons. Now, the diagram here shows all the gory detail. It actually ultimately takes 4 hydrogens, because we also need those neutrons in there. But the whole process starts with 2 hydrogens colliding together, and it ends with the production of a helium atom. So we went from an atom that had 1 proton to something that has 2 protons and 2 neutrons. So really, we had 4 protons to begin with, and we ended up with 2 protons, 2 neutrons, and some byproducts. Well, it turns out that if you weigh that original 4 protons, and if you weigh 2 protons and 2 neutrons, 4 protons weigh more than the 2 protons and 2 neutrons. So where did the mass go? Well, the mass turned into energy. Einstein was the one who came up with this idea that you can actually convert mass into energy, and that's what his famous equation is actually saying. E is energy, M is mass, C is the speed of light. And the speed of light is a very big number. In this case, it would be in meters per second, so that's 3 times 10 to the 8th meters per second. And then we're going to square that. So that's 9 times 10 to the 16th, which is a big number. So it does not take very much mass to get a huge amount of energy. And the mass difference here between the two is a very tiny difference. this picture kind of over exaggerates what's going on here. But that very tiny difference in mass is enough to produce a huge amount of energy. Now this may make you think, well, is the sun getting lighter? Well, sort of, but not by very much. The sun has been doing this for about 4.5 billion years, and I think it's something like less than 1% of the sun's mass has been converted to energy in all that time. So we're not talking about a significant change in the sun's mass. We're not talking about very much mass difference in this process. But it is enough to produce the tremendous amount of energy that we see coming from the sun. Now this hydrogen fusion process means we are using up the hydrogen. Now that's our fuel. Just think about your gas tank. When the sun first formed, we had a full tank. Well, it's been using up the hydrogen over time. And so over time, we're getting more and more helium and less hydrogen. This is roughly where we are today. And here we're looking at this region inside the dotted line is the core. So when we get to the point where essentially we have no hydrogen left, when the hydrogen runs out, that's when the sun dies. Now when we get into the section on the life cycle of stars, we'll find out what all happens when a star dies. But this is the transition point. When it runs out of hydrogen, when it's got a core full of helium, that's when the end begins. And so, as you can see, it's roughly another 5 billion years from today before our sun's going to die. So not too much to worry about. So for now, we are content to have a sun that is producing energy through this process of hydrogen fusion in the core.